Okay, let's get started here. So today we're going to start, well, we're actually going to start by picking up a couple of things that we didn't have time to get to last week about MCMC stuff. But then we're going to start to talk about our first actual application of this to social sciences, particularly it's, maybe most described in the article, its applications to political science, but really is more of a general approach for, research in general or, conclusions in general that integrate, not in the sense of like the opposite of differentiate, but combine different sources of information that may bear on the parameters of a model that you specify and you want the posterior distribution of. And this was, written down in a, people had ideas about this sort of thing before, but it was just sort of very systematically written down in a paper that's on the syllabus that you should definitely read for Thursday. But there was sort of a more introductory video discussion of the ideas in that paper, and it's soon going to be a book about these sort of things in a YouTube video that was on the syllabus. So this is maybe kind of an advanced paper to start with, to be sort of the first real application of Bayesian inference to the social science. Like bowling does not really count. But in past years and things like that, most other classes, they would probably start with a easier example of sort of applying this to social science with like maybe a one variable model or something, pretty simple like that. But for various reasons, we wanted to kind of dive in on this one first, more for its conceptual approach, but actually the code and the execution of it was by Stan and using MCMC. And so hopefully a paper like this gives you some or a lot of appreciation for how ambitious you can be, with Bayesian inference and Stan. So we'll get to that. As usual, I'm still an employee of Columbia University. Columbia has still received a bunch of grants to develop Stan. I'm still a co-founder of Stan Group, which is still doing a bunch of things promoting Stan with businesses. And according to Columbia University, that means I have to disclose these facts in presentations. So going back to where we ended last week, I tried to get through this, but I think I was actually talking pretty quickly. So we're going to try to do it again. So suppose you're interested in the expectation of some function, G. Could be a mean, could be a variance, could be a bunch of things. But let's say that's what you're primarily interested in. And you do MCMC to get a whole bunch of draws from this posterior distribution, so that when you want to estimate the expectation of G, all you have to do is mean of whatever function of the draws you want. And you get an estimate, which we'll call G bar, which is taken from the evaluations of this function for all the draws after the warm-up period. Stan has a pretty extensive warm-up period where it does a whole bunch of stuff, and then sort of turns on the tape and records all the draws from the posterior distribution after that. By default, it's like 1,000 after the warm-up period, but we're going to run multiple Markov chains in order to make sure they're all going to the same distribution. So we have draws of theta, we put them into the G function, we average over all the draws after the warm-up period, and Monte Carlo integration assures us that as the difference between M, which is the total number of iterations, and W, which is the number of iterations we throw away because it's the warm-up period, as M minus W gets large, this average converges to the true expectation of the G function, even though we can't do that analytically. But keep in mind, okay, we're going to be doing like at least 4, but even 8 would be better, separate Markov chains to make sure that they go to the same place. And, you know, we could calculate the average of this G function for each of the 8 Markov chains. And each time we're going to get a slightly different answer because they involve a finite number of random numbers. You take the average of some random numbers, it's going to be something. You take the average of a bunch of numbers that are supposed to come from the same distribution. They're going to be at least slightly different. And this idea of the Markov chain Monte Carlo central limit theorem gives us a basis for describing how much the mean of something could differ, you know, if we do one chain, and then if we do another Markov chain, we're going to get different estimates of the mean each time. How far apart could they be? Well, under some non-trivial conditions, this estimator, the average of a bunch of draws, it's going to have a normal distribution across chains. What's the expectation of that normal distribution? It's going to be the true expectation of the G function we're estimating. What's the variance, or what's the standard deviation of that normal distribution? Here, that's called the square root of V. But conceptually, it's the Markov chain Monte Carlo standard error. We want this to be small. We can estimate it. But, you know, the sort of non-trivial conditions are needed in order for the distribution of the mean to actually have a normal distribution across chains, particularly when we're estimating it, you know, not by doing like 50 chains, but just by doing some like single digit number of chains. So it's sort of non-trivial to estimate. It'll be done automatically, but you know, you don't have to worry about calculating it, but you do have to know conceptually what it is. And so if one draw of the Markov chain was independent of the next one, all these row quantities that we have the infinite summation of, those would all be 0. And the variance would just be the variance of the function divided by the number of draws that you're averaging over, which is how it gets its name. That would be the same phenomenon that you see with the central limit theorem for like frequentist statistics. But in the MCMC case, these rows indicating the correlation between draws within a Markov chain are not going to be 0. And so consequently, the Markov chain Monte Carlo standard error is going to be, you know, a little bit bigger than it would ideally be if we could obtain independent draws from the posterior distribution. So we want this Markov chain Monte Carlo standard error to be very small and validly calculated. That sort of gives us the assurance that we can say, okay, all these chains, they went to the same place. We'll just bunch them all together, pretend they came from like one chain, and then we'll describe that one chain however we want. But we need a small Markov chain Monte Carlo standard error to do that. So that's really all we're going for there. But the Markov chain Monte Carlo standard error, or the variance, which is the square of the standard error, makes an appearance in another important quantity called the effective sample size. So again, this relies on some non-trivial conditions. The number of warm-up iterations has to be large enough for Stan to do its thing. And the Markov chain has to move through the sample space sufficiently rapidly, sufficiently efficient way of doing so with minimal numerical error, etc., such that the Markov chain Monte Carlo central limit theorem I talked about on the previous slide actually holds. So that's sort of the non-trivial conditions that I sort of referred to. And in that case, we can calculate a quantity called the effective sample size, which we abbreviate N_EFF. So the effective sample size of a Markov chain That's what we're estimating there. And it depends on this estimate of V, which is the variance of the mean estimator, or the square of the Markov chain Monte Carlo standard error, which we said we wanted to be small. So what is this effective sample size? Effective sample size is a sort of abstract concept. It's not directly measured. But conceptually, it's the size of a sample from this posterior distribution that would give you the same amount of precision for estimating the mean as the number of dependent draws that you obtain. So I did not explain that very well. I'm going to try that again. So imagine you could take independent draws from this posterior distribution. You can't, but imagine you could. Effective sample size is the number of draws that you can imagine yourself taking from the posterior distribution that are independent, which gives you the same amount of precision in estimating the means of these G functions that you're interested in as the 1,000 or the 4,000 draws that you actually have from the posterior distribution that are not independent of each other. And so this idea of effective sample size, it gets its name because of a very similar idea in survey sampling. So we have simple random samples where you just draw independently, randomly from some population, and you like do a survey on those people. But that's very expensive. So what people actually do is like some kind of cluster sampling, stratified sampling, all kinds of different things that are less random than simple random sampling, because the people that are thus obtained are not independent of each other. So the one example of cluster sampling would be like randomly draw 100 zip codes. And then in each of those 100 zip codes, go randomly find 10 people. And now you have a survey of size 1,000. But within each zip code, the people are not independent. So the 10 people you get within each of those zip codes are not going to be independent of each other because they sort of live in the same area. And so you have to make adjustments, like finite sample adjustments and all these sorts of things when dealing with a cluster random sample rather than a simple random sample of 1,000 people from the entire population. So, you know, this idea of effective sample size also pops up in cluster sampling and stratified sampling and things like that, to take into account the fact that the people in your survey are no longer independent of each other because they were concentrated geographically or whatever it may be. So effective sample size is sort of a measure of how much your draws from the posterior distribution, which are not independent of each other, are worth. Like if you took 1,000 draws from, you know, what Stan gives you, and so the draws are not independent of each other, and you went to sell them on eBay, the price of those on eBay would be like 200, like you could trade that for 200 independent draws from the same posterior distribution if it were possible to obtain independent draws from the posterior distribution, which it's not. So it's sort of a measure of like the trade value of a hypothetical trade for like 1,000 draws that are not independent of each other for 400 draws that are independent of each other. And this would be a fair trade because they both, the 400 independent draws and the 1,000 dependent draws, give you the same precision in estimating this G function as each other. So it's sort of like a currency exchange rate between dependent draws and independent draws, but you can't actually get the independent draws. So it's entirely hypothetical. It's something we can estimate, but we can't, you know, exactly, make that trade. And so the effective sample size divided by the amount of time that it takes for Stan or another algorithm to run is a measure of how efficient the algorithm is. But it's not the only thing in part because you also need the conditions, fast moving through the parameter space and whatnot, in order for the Markov chain Monte Carlo central limit theorem to hold. And if the Markov chain Monte Carlo central limit theorem doesn't hold, then the estimator of effective sample size has no validity to it. The problem is we can't really verify when the Markov chain Monte Carlo theorem holds in practical applications. So in that sense, it's best to use like whatever is the most fast mixing through the posterior distribution algorithm you can, and that's Stan, at least in general. Also, like this effective sample size measure, there's one for each G function that you're interested in taking the expectation of. So they can be like bigger for one and less for another, etc. So it's not like an ideal way to measure like what algorithms are most efficient. But this effective sample size divided by time is one metric where Stan, really tends to do well, or at least as good as other algorithms. And Stan is very general. So there's, we're going to use Stan starting like next week, but not actually write Stan code until April. But while we're using Stan kind of indirectly, it's important to understand the advantages of it. So first of all, you as the user, you don't have to worry about like, is this conjugate with that, deriving a full conditional distribution, coming up with some special case algorithm that works on like this problem, but not on any other problem. All you have to do is write down the kernel of a posterior distribution in logarithm form. So that's really the only essential requirement placed on the user. Now that's the same requirement that's placed on the user of Metropolis Hastings. So, with Gibbs, you have to do some more analytical work to try to figure out the full conditional distributions. And oftentimes that's impossible. With Metropolis Hastings, you don't, but Metropolis Hastings is not a very effective computational algorithm, except in the case where maximum likelihood estimates are basically the same number as Bayesian posterior means. So in that circumstance, you might as well just do maximum likelihood. So the second advantage of Stan, particularly compared to Metropolis Hastings, is that it converges to the Markov chains that are done by Stan converge to sort of the heart of the posterior distribution very quickly, especially compared to other algorithms. And once they do, get to the posterior kind of the heart or the typical set of the posterior distribution, then Stan, it adapts things, for you, so you don't have to worry about this, but it moves through the parameter space for the variables you're trying to get the posterior distribution of very efficiently compared to Metropolis Hastings and oftentimes the Gibbs and any number of other MCMC algorithms that are occasionally used. And so you kind of have the best chance, if you're using Stan, of satisfying the conditions for the Markov chain Monte Carlo central limit theorem to hold. Now, that doesn't mean you can verify them, but you sort of have the best chance of being able to do that. And consequently, the Markov chain Monte Carlo standard error can be validly estimated. You can calculate effective sample size, all those sorts of things. Now, I said we can't verify whether things are going well for the Markov chain Monte Carlo central limit theorem to hold. However, if you're using Stan, it is possible to recognize conditions in which the Markov chain Monte Carlo theorem, Markov chain Monte Carlo central limit theorem, probably doesn't hold. So you'll be able to spot, and we'll learn how to spot these as long as you're paying attention, indications that there's a real problem here, and may be able to take some steps to remedy that. One thing that you'll find, and this may seem difficult to grasp without getting into the Stan language, which we won't do until April. But you can do sort of different, even if they're logically the same, reparameterizations of your posterior distribution. And you can get very different degrees of efficiency with which Stan will run. And this is one of the main reasons why we spent so much time talking about transformations of random variables. So like, this thing is gamma. And then how would we write down the PDF if we wanted to take the reciprocal of that thing and it's inverse gamma? So sometimes you can write down a model where the thing, it has like a gamma prior and it does badly. And then you just sort of change it up to be like the reciprocal of that. And it has an inverse gamma prior, and then everything goes well. Even though you didn't really do anything except like internally, do you call it gamma and then take the reciprocal of it? Or do you just start by calling it inverse gamma? There's no real like difference logically in the information. Conceptually, there's no difference in the posterior distributions, but one can be numerically a lot easier for Stan to do efficiently. And the other one, which is sort of logically the same, can be numerically difficult for Stan. And so we have to go through different ways in which we can like flip stuff around, make things easier for Stan without really changing the posterior distribution that we want to draw from. Also, the effective sample size, assuming that we get this well enough for the central limit theorem to hold, tends to be pretty high. High enough to obtain precise estimates of the thing that you're trying to estimate, even with only like 1,000 draws after the warm-up period per chain. So we do like 4 8 chains. Maybe we have an effective sample size of like 600 per chain. And so like 24,000 altogether if we do 8 chains. 24,000 effective. So just imagine, okay, what if I had 24,000 independent draws from this posterior distribution? Would I be able to estimate my thing accurately enough with 24,000 draws that were independent? If so, then we're good to go with what Stan gives us. In comparison to a lot of times you'll see Gibbs and Metropolis Hastings that have not nearly the same amount of efficiency. They'll do like 1,000,000 draws, because the effective sample size on their 1,000,000 draws is like 200 or 300. And they need to do 1,000,000 in order to get effective sample size of like 200 or 300. Whereas with Stan, you could do 1,000 and you're almost always going to get an effective sample size more than 200. So that's kind of how we measure it. It's relatively easy to use. It doesn't put a huge burden on the user beyond what the user should already be responsible for communicating, which is what posterior distribution do you want to draw from? What are your priors? What is your likelihood of these data? It converges quickly. It tends to go through the sample space efficiently enough for the Markov chain Monte Carlo central limit theorem to hold. And if it does, its effective sample size is usually going to be more than enough for you to estimate whatever it is you're trying to estimate with sufficient precision, even though you can't obtain the analytical pieces that you would need in order to estimate the thing with like infinite precision. So it's going to be close enough. Any questions about that sort of stuff? Yeah. So a lot of people have been asking me questions like, when do I use Metropolis Hastings? When do I use Gibbs sampling? The answer is never. Use Stan. And we're going to learn how the rest of the semester. Okay. So just as an overview of what I'll refer to as Humphries and Jacobs, which was a paper in 2015, but it's really a whole like project. So some of what I'm attributing to the paper might be sort of part of the broader project. But basically, the idea here And if you have any familiarity with political science, I don't need to tell you that for decades, it's been pretty sharply divided between, quantitative large N studies and, qualitative small N studies. And when I'm talking small, it could be like really small, like 2 or 1. The sort of deal where like you pack up and move to the country that you're studying and live there for like 3 years and write down everything you observe, and interviews and, reading history and journals and all sorts of things like that. A very sort of human intensive way of doing research as compared to what, a lot of people do these days, which is just like Google until you find a data set and then download it and start analyzing it. And you don't even have to like wear pants to to do research. But there's more than a little bit of division among political scientists as to like which of these two approaches to research is preferable, and like which is preferable in what situation, and the pros and cons of each. Psychology can be much the same way. We have these like very large surveys, and then we have, I guess, not 2 people or 1 people, but like sort of a small group, usually of like college students or whatever, who'll be part of a study that, it could be like a handful of students where they go like more in depth on like whatever psychological conditions, you may have, and then kind of report the results of it. It's more of a sort of narrative research style where like the researcher will ask questions and the person will kind of ramble on for a while and, try to divine conclusions out of the sort of verbal record of what's said. Within economics, there's probably more consensus that quantitative studies are the way to go, and they're certainly well represented in empirical economics journals, whereas in sociology, you kind of have more like the flip side of that. There are some large in sociological studies, but a lot of them tend to be, more of this qualitative research, case study sorts of approaches that sometimes resemble applied history, maybe a little bit more. So Humphries and Jacobs comes along and works out the implications under Bayes' rule of combining these 2 strategies of having like some or a lot of quantitative data on a relatively large number of observations. And within that set of, let's say, N observations, there's some subset where you go more in depth and do qualitative research on those to augment the data that you have, at least for some of the observations. And they work out the implications of that, and sort of explain how to do it in the context of political science. Now, it would have been possible, and arguably was done. Bayesians from many decades ago, like De Finetti or a bunch of other people, that probably could have described conceptually this idea of combining 2 different sources of information. Like from a Bayesian perspective, that's not all that novel conceptually. But the models that are described in the Humphries and Jacobs paper, which I abbreviate H and J here, would not have been easy to estimate prior to STAN. So in this case, the full conditional distributions are not going to have known forms. So you couldn't do Gibbs sampling, really. But there's lots of like inequality constraints and other things that make this probably not multivariate normal posterior distribution, particularly because you might only have like a few cases where you have the extra qualitative information. So if this is, not going to be well approximated by a multivariate normal distribution, because the sort of sample is too small, then like random walk Metropolis or Metropolis Hastings is not going to perform well. It's just not going to give good answers with any finite number of draws from this posterior distribution. So, in terms of doing this in practice, Stan was a really important piece to that puzzle, to sort of take these grand ideas and actually show how, almost any researcher could do this using Stan. But what arguably is the key to being able to use Stan is to have a research assistant who in 2014 took this class, Jesse Cooper. He knew a little bit of Stan coming in, but being able to work with, or not Jesse, Jasper Cooper, to work with somebody like that on a research project, really enabled the whole thing to get kicked off. And what you'll see if you sort of study this is that people don't spend a whole lot of time and effort in investing into like thinking about some model and what they can do if it's not feasible for them to do in practice. So it's just like if that's beyond the horizon, people don't really sort of seriously think about how I would do this. And so what you see is a lot of innovative models and like new theories and stuff like that coming up when there's some technological innovation that makes stuff possible that wasn't possible before. And Stan, I think, definitely deserves a lot of credit for being that innovation in this case. And so you see this sort of very sweeping presentation, and you'll read about it for Thursday paper on this idea of integrating qualitative and quantitative information to study something in the social sciences. So questions about that? Yeah. Okay, well, let's learn it. So Humphries and Jacobs starts off, and this can be generalized, but it's hard enough to understand even in the most simple case, with sort of 4 types of units. And in political science, these would often be like countries, but you could think of them as types of people or whatever your units of analysis are. And so let's say we have an X variable, which we'll think of as the treatment, and a Y variable, which we'll think of as the outcome, both of which are binary. And so all of our observations fall in one of 4 buckets. It's not like we can observe this, but conceptually they follow in buckets. So you can think of each country as having some unknown type. And here are the 4 types. So you can have countries that are adversely affected by the treatment, which is to say Y is always different from X. So if X is 1, Y is 0. And if X is 0, Y is 1. So switching a country from 0 to 1 on X causes them to switch from 1 to 0 on Y. And that's an adverse reaction to this treatment variable. So that's type A. Type B is countries for which treatment is beneficial. So Y is equal to X. So if X is 0, Y is 0. If X is 1, Y is 1. If you switch a country from 0 to 1 on X, you'd also switch them from 0 to 1 on Y. The third type, type C, is chronic. So those are countries for which Y is 0, irrespective of X. So if X is 1, Y is 0. If X is 0, Y is 0. This country is sort of chronically going to be 0 on the outcome variable and isn't affected by the treatment. And then the fourth type is type D, or units which are destined. So this is a country or a unit, whatever, for which Y is going to be 1, irrespective of X. So if X is 0, Y is 1. If X is 1, Y is 1. Y is going to be 1. Either way, and it doesn't matter if they get the treatment or not. They're just always going to be y equals 1. So those are the 4 types. They're mutually exclusive and exhaustive. Each unit of observation, country, person, whatever, has to be one of those 4 things if y and x are binary. But we don't observe directly the type of each country. In particular, if we organize this into the famous 2x2 table, what you'll see in each of those interior cells is there's going to be ambiguity. So let's say we observe a country for which x is 0 and y is 0. Well, that's consistent with the country being type B, or it's just as consistent with the country being type C. So it could be the case, we observe a country where x is 0. If we changed x from 0 to 1, y might change, but we don't really have the ability to do treatments on countries and see what happens. So we just sort of observe. This is mostly for observational data, which is pretty common in political science. So we observe in reality, in history, x was 0. But we don't know what would have happened if that same country had instead been x equal 1. And so we see x is 0, we see y is 0 for that country. That country could have been a beneficial type, in which case if x had been 1, then y would have changed to 1. Or that same country could be just the chronically y equals 0 type, that even if you changed x from 0 to 1, y would have stayed 0. And so we can't tell just by looking at history whether this country where x is 0, y is 0 is a type beneficial or is type chronic. And it's the same with the other 4 cells. So if we observe x is 0 and y is 1, that country could be adversely affected by treatment, or it could be destined that y is 1 for that country. And if, in the bottom left, if x is 1 and y is 0, it could be the country is adversely affected, or it could be the country is chronically y equals 0. And in the bottom right, x equal 1, y equal 1, well, the treatment could be beneficial, or the unit could be destined to be 1. We can't tell just by observing the historical data. And so this is sort of a fundamental problem in attributing how much of an effect does this treatment have, because the data themselves can't tell you, which countries are B, which countries are C, among which, where x is 0 and y is 0. So does everybody see the problem? Or, Adam?
So this is a fairly common kind of, this isn't specific to Humphries Jacobs, right?
Yeah, Don Rubin may have claimed to have said it before. But yeah, so.
It seems similar to me to always takers, never takers.
It is. It is. I mean, somebody may have said that before Don Rubin too, but yeah, there's not that many ideas in statistics. But does anybody have questions about sort of what the problem is? We don't really see the types. We just sort of can narrow it down to 2 types are possible for each thing that we see. And we're trying to figure out the causal effect of x on y. That puts us in a pickle. All right? We're good so far? Okay, so then we have this vector lambda, which is a simplex. It's non-negative and sums to 1, that contains the true proportion of each of the 4 types in the population or the world, whatever you're considering to be the domain of your research. So lambda A is the proportion of countries that are type A. We can't observe what that is directly, but it's just some unknown quantity that we want to estimate. Lambda B is the proportion of countries that are type B. You got type C, type D, etc. These are non-negative, and they add up to 1 because our 4 types are mutually exclusive and exhaustive. So it's the proportion of each type in the population. And consequently, conceptually speaking, the average causal effect of this treatment variable on this outcome variable is lambda b, which is the proportion of countries for which treatment is beneficial, minus lambda a, which is the proportion of countries for which this treatment is harmful. That's something we can conceptualize about, but we can't observe directly. But sort of the average effect of this treatment is going to be the proportion of countries that are beneficial minus the proportion of countries for which this treatment is adversely affecting them. So that's the concept that we're trying to get here. And we need really the posterior distribution of lambda A and the posterior distribution of lambda B in order to do that subtraction and get an estimated posterior distribution of the average causal effect of this treatment on this outcome. So this is really the key quantity of interest that we want to get the posterior distribution for. And, you know, we can't just go out and observe it. In general, you can never go out and just observe average causal effects. You're always going to have to make assumptions and stuff like that in order to estimate them somehow. So we really have this mathematical concept of lambda b minus lambda a. And we want to try to, you know, get data, get a posterior distribution, and get after this quantity. So what particularly qualitative researchers do, and what Humphries and Jacobs is imagining they do, is to go out and seek auxiliary data besides X and Y. So X and Y are sort of thought of as like cheaply obtained data. You can just sort of like look on Wikipedia and you could probably get like the X and the Y for a bunch of countries. But then you need to seek auxiliary data, which requires you to go beyond looking something up on Wikipedia to find what's known as the clue or clues, which are abbreviated K in the presentation and the paper, that help. There are additional information that gives you more leverage, at least probabilistically, on, you know, which of the two types that a country could be, you know, after we've observed its X and Y. So we know which quadrant of this table here the country falls in, but we don't know whether it's like B or C. We need a clue that helps us distinguish, at least probabilistically, is this more likely to be a type B or more likely to be a type C, or, you know, whatever the other combinations are. So we need something K beyond X and Y to give us more information about each country's type. And we just sort of need a little bit of information to start to tip the scale and be able to like estimate this average causal effect. Maybe not as precisely as we would like, but you can at least estimate it if you synthesize this data on the clues, which are like expensive to go out and get, with the sort of cheap data on Y and X that you can readily obtain a lot of observations on. All right. Questions about the process so far? Okay. So the next idea we need to talk about is the so-called probative value of a clue. And so this is a term of art in the qualitative research literature. But let's imagine this thing phi, which is indexed by J and by X. So conceptually, this is the probability that the clue variable is 1. Again, the K is also binary. It's either 1 or 0. So the conditional probability of observing the clue, conditional on the country being of type whatever, type A, type B, type C, type D, and conditional on X. So it's a conditional probability of observing the clue for a country of this or that type that has this or that value on the X variable, and we observe X. So that's what phi is. Yes?
Before we go forward, we go back to the last one.
Always can go back.
So here, we don't, like, for a country, we know, like, if it's in the first cell, X0, Y0, like, we don't know if it's B or C.
Correct.
So we haven't observed when we gave it X equal to 1.
Correct.
So we have some, that is the unobserved data.
Right. We don't. If we could observe a country like simultaneously that was x equals 0 and x equal 1, we wouldn't have this problem. But then we would have like a time travel problem, because you can't observe a country in the x equals 0 regime and the x equal 1 regime simultaneously. About as best we can do is sort of look for events where x changed from 0 to 1 rapidly, and hopefully exogenously. But yeah, I mean, that's a whole nother problem. So yeah, you can't just look at history and figure out the types. But you can expend some more effort, get at least a little bit of data on K. And then I'll say conceptually, we have these phi variables, their conditional probability of K given J and X, where J is the type. That can be A, B, C, or D. And then we can define the quantity, for example, phi subscript Bx minus phi subscript Dx, and call that difference the probative value of this clue given that X is equal to 1, whatever it is. So B and D, you'll remember, are the ones in the bottom right here. So let's say we observe X equal 1, Y equal 1. We don't know whether the country is B or D, but we observe some clues, and that gives us some probative value of the clue for discriminating whether this country is like probably type B or probably type D. So the difference between phi Bx and phi Dx is the probative value of the clue for that value of X in terms of discriminating type B from type D. So in terms of classification, we can say this sensitivity is the proportion of K equal 1s that are correctly classified. And we have specificity, which is the proportion of zeros on the K clue variable that are correctly classified. So I'm just going to skip ahead to this figure from Humphries and Jacobs, which is a really important one and sort of tells the story of this. So let's say we have some clue that we have data on, and on the horizontal axis, we have phi D. So the phi value, let's say X is equal to 1, doesn't really matter, phi D 1. And then on the vertical axis here, we have phi B 1. So D is on the horizontal, B is on the vertical. And the probative value of the clue is the difference between the vertical and the horizontal. So if we're along the diagonal here, where there's a dashed gray line, this clue is useless for discriminating whether a country that falls in like this bucket is type D or type B. But as you go off the diagonal in any direction, you start to get some more leverage on, okay, I observed X is 1, Y is 1, and I've observed the clue. If the clue has probative value, now you started to get some more information, and that's going to map onto the posterior distribution in terms of what is the type of this country. And if you can get it's all a question of degree, but if you can get like a really good clue that sort of takes you, either to the top left or the bottom right, that's like a really awesome clue because, when you observe it, you have a lot of information about the country's type. Now, you're never going to be completely sure. There's no perfect clues, but, the more probative value you can get to the clue by getting away from the diagonal and into the top left or the top right corners, the better off you are in terms of leveraging information about, units and being able to estimate the lambdas as part of your posterior distribution, and then calculate the difference between lambda B and lambda D, or lambda B and lambda A, to get the average causal effect of this treatment. So the bad clues are going to be on the diagonal. Good clues, if you can find them, will take you off the diagonal, and that is said to have a lot of probative value. There's also a lot of, frankly, weird phrases that apply depending on which part of the square the clue lands you in, like straw in the wind and like smoking gun and hoop test. Those are all explained in more detail in the paper when you check those out. But again, those are sort of historical phrases that give us sort of a typology of clues. But really there's like clues with low probative value and clues with high probative value and anywhere in between. It's a continuum. Questions about this figure? Yeah, yes.
Can you explain the difference between, what's the difference between being more sensitive or here more specific?
Yeah. So sensitivity is, a situation where given, the type J and the X, we could get all the K equal ones, we could guess those right. So if we knew, again, none of this is observable, but possibly estimatable. Like if we knew your J and we knew your X, how sure could we be that you're a 1? And the same thing with specificity, the proportion of zeros that you can get right conditional on what you condition on. And clues can be more sensitive or more specific in terms of their ability to get you the information you're looking for.
So that's like type 1 and type 2 errors essentially?
Yeah, well, both the type 1 and the type 2 errors are sort of like misclassification.
Right.
So you thought the null hypothesis was true, but you were wrong. It's the same sort of deal here, except there's no real null hypothesis yet. It's just like conditional on a country's type, which you can't observe, and their X, which you can observe. How good would you be at guessing, is the clue going to be 1 or is the clue going to be 0? And how often would you be correct in each case? Good?
So how is this different from just classification algorithms?
Well, it's only an idea because we're conditioning on the type J, which is unobservable. Like the typical like machine learning classification stuff, it's just conditioning on observed data. But we've defined the type as unobservable. So this idea of specificity and sensitivity is really just a concept, but depending on whether you go like vertically or whichever direction you go in this, you get sort of more sensitivity or more specificity. And if you manage to get like up into the corners, then you get like both. And so that's good for the purposes that you're trying to do it. But to say like, how is this different from like, random forests or whatever? Those sorts of algorithms only condition on observed information. Here we're talking about a concept for a conditional distribution, conditional on something that we've just said we can't observe directly. So this is all sort of a indirect way of getting at these ideas, but then we're sort of directly going to get the posterior distribution. So, we have estimates of stuff.
And that itself of a clue. So it's from where we observe the clue to classify something as.
Yeah. So, if you're on the diagonal, you've wasted your time and effort getting these clues because they don't tell you anything about the two types, irrespective of, whether the clue is observed or not, or K equal 1 or K equal 0. Okay, so how might we translate this into, math? So we're going to have another set of quantities, pi, which are also indexed by type. So type A, type B, type C, type D. This is the conditional probability that X equal 1, conditional on the country's type, which is still unobserved. So there's 4 of those because there's 4 types. So the probability that X equals 1 given the country is type A, probability X equal 1 given that country is type B, type C, type D, etc. So we can sort of think, the idea here, at least in imagination, is, okay, you get some quantitative data on X and Y, that's pretty easy. You select randomly a subset of cases where you go to the time and expense to look for the clue data. And so you have like maybe half or perhaps less, whatever, observations where you have the clue data, and the other half of the observations, you didn't even look for the clue because it was too expensive for you to do that. And so you can think of the clue data that sort of exists in reality, but you didn't seek it out to collect as missing data. And we're going to have a week about missing data sometime in April, where we'll talk about this more. But you might have heard the phrase missing completely at random, which would apply in this situation if you do sort of simple random sampling of the cases where you have both X and Y to go out and look in that subset for the clue. Now, that's not what happens in reality. People tend to choose countries to like look for the clue that they want to visit, or like other reasons. They tend not to go into a country where there's like a civil war going on. So, it doesn't exactly work this way in practice. But just sort of imagine you say, okay, I have 40 countries that I have X and Y on. I want to select 20 where I'm going to go look for the clue. I'm just going to take a simple random sample of 20 out of my 40 and go do that. So first we're going to talk about the observations or the cases where the clue is not sought. That's different from k equals 0. So k equals 0 is when you look for you go to the country or whatever, you do qualitative research, and you conclude that k is 0, like you observe k to be 0. Here we're talking about cases for which you don't even go look. So you don't know whether k is 0 or 1. But we can write a multinomial likelihood for those cases that's going to have 4 possibilities just based on the 2 squared combinations of X and Y, which are both binary. So the 2x2 table. And the multinomial likelihood can be written as, the product from 1, 2, 3, 4 of W's, which are probabilities, raised to n, which are the number of cases that you observe falling in that bucket of the 2x2 table. So we can think of these as vectors of length 4. So n, the vector, is the number of cases where X is 0, Y is 0, and you don't know what the clue is. N01 is the number of cases where X is 0, Y is 1, and you don't know what the clue is. N10 is the number of cases where X is 1, Y is 0, and you don't know what the clue is. And N11 is the number of cases where X is 1, Y is 1, and you don't know what the clue is. So each of these n's appear as exponents in the multinomial likelihood, and the probability, which is the base that's being exponentiated, the w's here are sort of the conditional probability of falling in each of the 4 regions of the 2x2 table. So these w's are conditional probability of X is this, Y is that. We don't know what K is. Conditional on lambda, which is that simplex vector of length 4, and pi, which is this not a simplex vector, but a proportion or a probability that X is 1, conditional on type. So pi does not sum to 1. It's not a simplex vector. It's just a vector of numbers between 0 and 1 that doesn't sum to anything in particular. So this conditional probability W is given by a function of lambda and pi. And so what is that function? The first element of W, so W 0, 0, the probability that X is 0, Y is 0, and you don't know what the clue is. Conceptually, that's the probability of being type B or type C. And because B and C are mutually exclusive, we don't have to worry about like subtracting the probability of them both being true at the same time. And we can express the probability of being B or C in terms of various elements of lambda and pi. So the first one here is lambda B, which is the proportion of countries that are type B. We don't know what that is, but we're going to estimate it. Multiplied by the probability that X is 0, given that you're type B. So that's 1 minus pi B. So that covers the B case. And then because it's the probability of B or C, we have to pick up the C part, which is the proportion of observations that are of type C multiplied by the conditional probability that X is 0, given that you're type C, which is 1 minus pi C. So it's, to just sort of rephrase this, it's the overall proportion of type B countries multiplied, in order to take the subset, of those where they are type B, but X is 0. So that's if pi is the probability that X equals 1, given your type, 1 minus pi is the probability that X equals 0, given your type. And so we just multiply the lambdas by, pi b, or in this case, 1 minus pi b, to get the probability of you being a particular country being type B. And then we add to that the probability the country is type C that's implied by the rules of probability. So we can do that for each of the 4 buckets of W with like different expressions here. And it can be shown that this W is a valid simplex vector. It's not lambda alone. It's a function of the lambdas and the pi's, but it comes out to a simplex vector. And consequently, that's what you stick in as the parameter to the multinomial likelihood. So you've got your W's and you raise them to the power of the n's, and you can evaluate the multinomial likelihood for these observations where you have the X and the Y, but you didn't even go out and try to find the clue. So we have a multinomial likelihood, and we have a way of constructing, given lambda and pi, the input, the parameter to the multinomial distribution. And this is why we practice with the multinomial on the last homework. So we'd be ready for this. All right. So there's some function, let's call this the W function of lambda and pi, that spits out, the probability of falling in each of the 4 regions of the 2x2 table. That's all. It's a slightly tedious function, but it's not like it's real complicated. Questions about that? Okay. So now we can go on and consider the multinomial likelihood for the observations where we sought clues. And so sometimes we actively observed k equal 1, and sometimes we actively observed k equals 0. Consequently, there's now like more combinations of stuff to worry about. So we'll let, for these observations so we've got these fees. Again, they're indexed by J and X, and we can sort of collect them into a vector for organizational purposes if we want. We have phi A 0. So that's going to be the probability that k equals 1, given that the country is type A, and we observed X equals 0. And then next to it, we have phi A1, the probability k equals 1, given that a country is type A and X equal 1 was observed. And so we do that for the others. There's 8 fees here for each country. So we round those up. And the cases where a clue is sought, there's now 8 possibilities, 2 to the 3rd power, because k is binary, x is binary, and y is binary. So now we have to do a multinomial likelihood involving 8 categories for the intersection of x, y, and k. So the W, or the N, the N's now is the N with the dots over it. This is a vector of length 8. The number of cases for where you sought the clues, the number of cases that fall in each of the 8 buckets for x, k, and y, all those combinations. So we have some number of cases, maybe 0, in each of those strata. And then we have a different W function, which is going to depend on lambda, on pi, and on phi for the situation where the clues are sought. So we have the probability that you are B or C and K equals 0. So the and K equals 0 applies regardless of whether you're B or C. So top left bucket and the clue value comes up 0. And there's an expression for that in terms of lambdas, pi's, and phis. And so there's 8 of those that if you sort of work it out carefully, you get all this. And the thing on the right here is also a valid simplex vector for those observations where you sought clue data, and consequently you need a multinomial likelihood that's the product of the w's raised to the power of n for each of the 8 possibilities. But n equals 0 is valid. You're just raising something to the power of 0, so you multiply by 1. So that's okay. So there's really up to 8 ways in which the variables could fall when you collect x, y, and k. And for each of those 8 like combinations and stuff like that, we have a corresponding expression that gives us the probability, according to the model, of that holding for each observation. And then we count up all the observations that fall in this. That's assuming the countries are conditionally independent, which oftentimes that may be kind of a dubious assumption, particularly if the countries are like neighbors or they have a lot of trade with each other or things like that. But let's just assume they're conditionally independent, and we can evaluate this function too, which gives us the simplex vector we need to put in to the multinomial likelihood. So we have a likelihood for the cases where the clue is not sought, which is a little bit simpler. And then we have a likelihood for the cases where the clue is sought, which is definitely more tedious, but it's not like we're talking rocket science here to evaluate the thing on the right. It's just algebra. It's not even algebra. It's like evaluating an expression with like random variables that we have beliefs about. All right. So with those two things together, we cover the likelihood. And now all we need are priors. So in the sort of baseline model that Humphries and Jacobs talks about, we have these sort of 2 different multinomials, one with 4 possibilities, the other with 8 possibilities. This is sort of a way of describing posterior distribution. So you usually start with what you're assuming about the likelihood. So the n's are multinomial, and the parameters to that multinomial is the corresponding w that's the simplex vector for that case. Okay, what's w? Well, all the w's are a function of lambda and pi, or maybe lambda, pi, and phi that were given on the previous 2 slides. Okay, so we've accounted for the w's, but the w's involve the unknown lambdas, pi's, and possibly phi's. So we need a prior on expressing our beliefs on each of those. So let's write lambda as equal to gamma divided by the sum of the elements of gamma. So both lambda and gamma are vectors of length 4. Lambda is a simplex. Gamma is just some positive random variable. And if we divide the gamma by the sum of the gammas, that implies lambda is going to be non-negative with a sum of 1, which is a simplex vector. Okay, that accounts for lambda, but what about gamma? So gamma is going to have in the baseline model, a gamma 1, 1 prior, which implies the distribution, prior distribution on lambda to be Dirichlet with like all the shape parameters of the Dirichlet distribution equal to 1, which we mentioned a couple times ago, weeks ago, that's assuming that's a uniform prior over the space of simplex vectors. So all simplex vectors of length 4 have equal probability density regardless of what lambda is. Okay, so that covers the the W's, the lambdas, and the gammas. All that leaves us are the pi's, which is the probability that x equal 1 conditional on your type, and the phi's, which is the probability that k equals 1 conditional on your type, the country's type, and the country's value of x. So there's 4 pi's and 8 phi's. And each of those have independent beta priors in the baseline model. And so, okay, if those have beta priors, you need to choose the alphas and the betas for those. But we learned a little bit how to do that. You know, you could think about the mode and you could think about the median that you believe sort of prior to seeing the data. And you could solve this system of 2 equations for, you know, alpha and beta, and then you know what values of the shape parameters for the beta distribution you should use, what like numbers you should use for alpha and beta to describe your beliefs, prior beliefs about pi or about phi in terms of a beta distribution. And now you've sort of closed it off. You have a likelihood that depends on W. You have a function that tells you the W's that involves lambda, pi, and sometimes phi. You have an expression deterministically relating phi to gamma. You have prior beliefs about gamma, which is a gamma prior. And you have prior beliefs about pi, which is a beta prior. You have prior beliefs about phi, which is also a beta prior. All you need to do is choose the shape values, particular numbers for these beta priors. And you can do that by thinking about your prior mode, prior median, and solving a system of 2 equations. And now you've fully described your priors and your likelihood. All you have to do is like write this in terms of in PMFs and PDFs, take the logarithm of it, and it's ready for Stan. So we're about out of time today. I have one more slide which actually sort of expresses this in terms of F's and whatnot, but this is really just a restatement of the more kind of verbal description of the priors and likelihoods on the previous slide. So I'll put all this up on Courseworks later. But, you know, that's how you have to sort of have a model for the data generating process in terms of like probabilities and lambda and pi and phi and all that sort of stuff. Figure out according to your model what that implies in terms of the likelihood of observable data. So those were the W functions that we talked about. And then express your prior beliefs about everything that's unknown. You know, write that in terms of PDFs and take the logarithm. So now it's in like log PDFs. Condition on the data that you actually observe. Use Stan to get draws from the posterior distribution that's implied by all this. And now you can describe your posterior beliefs about any quantity of interest you want, which in this case ultimately is the difference in the posterior distribution between lambda B and lambda A. So we're gonna do all that just to get the posterior distribution of 2 things. And we're gonna take the difference of those. And now we have our beliefs about the average causal effect of X on Y that's implied by our prior beliefs about all these unknowns, and the likelihood, which is sort of the mechanism by which the unknowns have a model that generates the observed X's, the observed Y's, and the observed K's that we see when we go out and seek the K's. So we're able to combine a relatively lot of information on X and Y with relatively little information on the cases where we sought K to get more stuff to condition on in order to get more useful and updated posterior beliefs about this. Because our prior for lambda b minus lambda a is going to be centered on 0, because both lambda b and lambda a have the same prior expectation. But conditional on the data, we're going to be updating our beliefs, and now we may believe that this x does have average causal effect, and that's research at the most basic level, having a logically consistent in terms of probability way of describing how the data are generated, your beliefs about these unknowns, and technology that allows you to draw from the posterior distribution, and then describe the draws for this difference, which is the thing that you are aiming at. And you might not even care about the rest of the posterior distribution if it allows you to really directly answer your research question that only involves lambda b and lambda a. So in that sense, it's a very ambitious yet withstand reasonably straightforward way to do research, particularly in the social science, particularly political science. But honestly, if you just sort of generalize the examples in the Humphries and Jacobs paper, you could do anything that has sort of multiple sources of data, some of which are relatively cheap to get, others of which are more expensive to get. And so you can't get the expensive data for everybody, but you may be able to get it for some of the cases. Anyway, we'll talk more about this on Thursday.
For the non-social science people, just to get familiar with some of the inference tasks we want to do here, or the prediction task, I don't know what to call it. What source should I read?
I'd say the paper.
The paper? Paper has enough basics to just help us understand it.
Yeah, I mean, it's written for a pretty general audience.
Right.
What's happened here? I gotta turn this off here. And
Are you broadcasting live?
yes,
Oh.
at least it says I am.
It's fun. I was thinking you could also do online PA hours, office hours.
Yeah,
That would be a nice thing that people don't have to come all the way. You can just stand in queue, sort of online queue, and just you can answer questions one by one.
yeah. More often do it with just you take a 15-minute appointment, but we can do it online. So if you want to do that,
I can
sign
email
up.
you.
Yeah.
Okay. The other thing was so you said there were at the very end you were mentioning a few inference tasks that we could do using this technology, which is one was you wanted to do, estimate this average causal effect. Could you explain why we do the minus thing? The average causal effect?
Yes.
Or is that